Hello students, welcome to this lecture number 3 on states of matter. In the previous lecture we have discussed about the two very important gaseous law, that is the Boyle's law and the Charles law. In this lecture we are going to discuss another two very important law. First we will discuss the Amonton's law and then we will discuss the Avogadro's law. So, heading of this video, that is the gas law. Gas laws, and that is basically we are going to discuss the two specific laws, that is the Amonton's law and Avogadro's law. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. First we are going to discuss the Amonton's law. Amonton's law is basically the relationship. It tells about the relationship between the constant volume, that is between the pressure of the gas and the temperature of the gas. How with the increase or decrease of the temperature, pressure is going to be affected at constant volume and the fixed amount for the fixed amount of gas. What it states that it states that 1 degree increase or decrease of the temperature, how pressure will going to be affected, going to change, or this will be increase or decrease. That is, they say that is 1 by 273.15 of the original pressure at 0 degree Celsius, and it is at constant volume and fixed amount of gas. So how the pressure is going to be affected with the increase or decrease of the temperature, that we can understand from this Amonton's law. And mathematically we can express this Amonton's law like this way. Suppose we have to assume it. Suppose the 0 degree Celsius, the pressure is P0, and at T degree Celsius, pressure is Pt. So we can say Pt is equal to, that is P0 plus P0 by, that is T by 273.15 into P0. So we can write this equation P0 1 plus T by 273.15, and this can be further written, that is P0 273.15 plus T by 273.15. And this relationship can be further expressed in this way. We know that is in the Kelvin scale, we can write this 273.15 plus T, and T0 is equal to 273.15. So we can write this equation in this fashion, that is P0, that is we can say Pt is equal to P0 into this. So it can be further says Pt by this is equal to T0 by T0, or this can be further says P by T is equal to constant. So from this we can say P by capital T constant. P is directly proportional to the capital T. So we can say from this relationship that at constant volume and for the fixed amount of gas, the pressure is directly proportional to the absolute temperature. We can write, and this is the Amonton's law. And this law can be graphically represented. Suppose in the x-axis you are given the absolute temperature, in the y-axis you are given P at that time. So what we get? So what we find, there is a relationship at the constant volume for the fixed amount of gas. You can say the pressure is directly proportional to the temperature, and the graphical representation of this is, it is a straight line, and where you can see for the constant volume, that is here V1 is greater than V2, V2 is greater than V3. Why it is so? Because when the pressure is decreases, then volume will be increases. Naturally this V1 will be greater than this V2, and because there is a, as per Boyle's law, we know pressure is inversely proportional to the volume. So we can able to understand the graphical representation, and now we are going to discuss the logarithmic expression of Boyle's law and Charles' law. Expressions for the Boyle's and Charles' law. And let us first understand Boyle's law. Boyle's law, we know PV is equal to constant. So if we take the log, it is log P plus log V, that will be constant. And now we take this log V, we can write the minus log P plus constant, and this equation you can see that is the equation of a straight line, because you can see y is equal to mx plus c. Y axis, y is equal to mx plus c, and this is the equation of the straight line. So here m is basically the slope, or you can a gradient. You can see is the gradient is minus, it's a negative gradient, and this is a constant. So if we plot this graphically, what we found, it will be coming like this. This is, so you can plot this log p in the y-axis and log b in the x-axis. So this is the logarithmic expression of the Boyle's law and the graph for this logarithmic expression. Now we will understand for the Charles' law also. Charles' law, we know that is basically, what is Charles' law? V by T is equal to constant. So log V minus log T is equal to constant. So we can write log V is equal to constant plus log T. constant plus log t. So here also you can see that this will be the straight line, but difference from the Boyle's law is that it will have the positive slope. So we can write this equation will be like this, where in the log v in the y-axis and log t in the x-axis. Sometimes question asks in the IIT JEE, what is the graph? Different graphs will be given. You have to select among those graphs which is actual logarithmic expression for the Boyle's law or the Charles law. Now we are going to discuss another very important law I should say, that is the Avogadro law. Now we are going to discuss another very important law, that is Avogadro law. Avogadro. Avogadro, while combining the conclusion of the Dalton's atomic theory and the Getz-Luxach law of combined volumes that we have already discussed in the first chapter, that is the fundamental of the chemistry, he proposed this law. This is famous as a Avogadro's law. What it says? It says that for equal volume of all the gases at constant temperature and pressure, it contains equal number of molecules. This means we can say that at constant temperature and pressure, as far as the volume of the gas is concerned, it depends on the number of molecules. Means it will depend on the amount of the substance in the gas, or we can say it is depends on the moles of the gas. So we can write the mathematical expression of the Avogadro law is like this. Suppose V is the volume of the gas, and N is the moles of the gas. So we can write this: V is directly proportional to the N. V is directly proportional to the N, and so you can write this: V is equal to Q4 into N. So Q4 is a proportionality constant and N is the moles, number of moles. And 1 mole of gas contains, that is 6 point, or we already know that 1 mole of gas contains 6.02 into 10 to the power 23 numbers of molecules. And it is called the Avogadro number. Avogadro numbers. And for a STP, we know there is two things. That is, one is STP and another is NTP. What is STP? STP is basically the standard temperature pressure. It is called standard temperature, standard temperature and pressure. And in the standard temperature and pressure, the volume of the gas is constant, fixed for every type of gas, and it has been found, this is 22.41 liter. And what is the standard temperature? Standard temperature, we know the temperature is 273.15 degree 15 Kelvin and pressure is 1 bar. This we will call the standard temperature and pressure. And NTP, what is NTP? NTP is normal temperature and pressure, and at that time T will be 273.15 Kelvin and pressure will be 1 atmosphere, and its volume will be standard temperature pressure, that will be 71 liter, but here standard NTP, that will be 22.41 liter. So this is a very important statement, and we have to always keep in mind that this will help in solving lot of numericals. Now from this Avogadro's law, this is a very important statement. We can able to prove that molecular mass of the gas is directly proportional to its density. That we can able to prove from. So from Avogadro's law, it is volume V is equal to K4, that is proportionality constant, into N, and N we know that is mass of the gas, suppose it is small m, and molecular mass, that is a capital M. So we can write this N is small m by capital M. We just put here, we can find V is equal to K4 into small m by M. So what you will just rearrange this equation, you will get molar mass equal to K4 into small m by V, and small m by V, we know this is a density, so we can write this M is equal to K4 into V. So we can easily see that density is proportional to the molar mass. This is a very important equation. It will help us in solving many numericals. Now we will solve one or two numericals which will able to help us to clear our concept. This is a numerical that you can see. A sealed tube. Suppose this is a sealed tube. In the sealed tube, it has the capacity to withstand the 3 atmospheric pressure, and it is initially filled with the air which is having the 23 degrees Celsius temperature, and it is having the pressure is 760 millimeter of H. So you have to tell the temperature above which the tube will burst. How the tube will burst? Now as we increase the temperature, the pressure will increase, as we already understand from the Amonton's law. And at the time will come when the pressure will be above this 3 atmosphere, because this sealed tube can withstand 3 atmospheric pressure only. So after this it will burst. So we have to see in which temperature this is going to happen. So for that, what we will do, we have to take the help of this law. P1 by T1 is equal to P2 by T2. That we already discussed in the Amonton's law. And here you can see P1 is given what? The 760 millimeter. And what will be P2? P2 will be 3 into 760 millimeter, because 1 atmospheric pressure is equal to 760 millimeter of Hg. And you have given the T1
T1 in 27 degree means 273 plus 27. That will be coming around 300 K. So we have to calculate the T2. To T2, how we will calculate? T2 is equal to P1 by T1 T2 is going there, so this will be P2 by P1 into T1. Now we will put this value 3 into 760 millimeter into T1 is 300 divided by P1 is given 760. So this will coming around 900. 900 carefully, but you have to answer in the Celsius. So T is basically will be 900 minus 273 and it will be 627 degrees Celsius. So this will be the answer. So at 627 degrees Celsius, the tube will burst. This is another numerical you can see. A gas occupied a volume of 250 milliliter at 700 millimeter of Hg pressure and 25 degrees Celsius. An additional pressure is required to reduce the gas volume to is 4 by 5 of its value at the same temperature. So additional pressure when you give pressure, the volume will be reduced. Matlab you have to increase the pressure. So when it is the same temperature, it means that will the Boyle's law. You have to solve it from the Boyle's law. In the Boyle's law, we know that P1 V1 is equal to P2 V2. Okay. So we have to see from this numerical the value of P1. P1 is given 700 millimeter H. And V1 is given here that 250 milliliter. You have to calculate the P2 and V2 is given 4/5 of the value of the original 4/5 of the volume of this means 250 into 4 by 5 it will be 200 milliliter. Means that how much pressure you have to give so that the 250 milliliter of this content of the volume of the gas becomes 200 milliliter. So what pressure you have to give? Now P2 we can calculate P1 by V1 by V2. So you have to 700 into V1 is 250 and you have to this 200. So we will get this 35 . So how much it will? That will be 875. This means that additional pressure you have to give, that is 700 minus that is 875 minus 700, that will be 125 millimeter. This will be the answer. So when you give the 120 millimeter additional pressure, that is 875, then at the time you will get the volume, that is 4/5 of the volume or 4/5 of the original volume. Okay, that is all for today's lecture. In this lecture, we have discussed the very important two important laws, that is Amonton's law and the Avogadro's law. Hope you that all the things that clear to you. If you have any doubts, you can comment in the comment section. Thank you for watching, and the next lecture we will discuss about the ideal gas law, ideal gas equations. Thank you very much for watching.